Hello, everyone. This is a presentation on APISAN. It's a tool about sanitizing API usage through semantic cross-checking. This was done by a group of graduate students at Georgia Tech and presented by myself, Jeremy Neal. So just a quick outline for the presentation. This the main sections we're going to cover. And real quick note, there will be a pop quiz somewhere in here, so be ready, stay on your toes, and see how you do. So let's just quickly go over the problem statement, kind of what API SAN is hoping to solve. So the main problem, or one of the main problems, is that APIs and their documentation can be complex and extensive. So it's not always very clear. One small misuse can cause a very serious vulnerability. We will look at a couple real examples and bugs, and a couple sample exploits to kind of show the impact. Developers can implement the same API calls differently. That's kind of the crux of the main issue that this paper is looking at and this tool is trying to solve is that using the same function call can be done differently and implemented differently. So it'll take a look at those. And developers make mistakes. That's a big problem, and API SAN hopes to solve that and find some vulnerabilities. So a quick overview of the workflow. You can almost think about this like training an ML model, except it's not. This paper was from 2016, so before the whole AI craze. But what it does is it looks at a bunch of source code, OpenSSL, Linux, Python, huge open source projects, millions and millions of lines of code, and it builds symbolic contexts. We'll look at that in about 2 slides, but it looks at these functions, it looks at the API calls, it tries to break them down semantically to find similarities, and then it tries to kind of infer the correct usage based on uses kind of a majority rule system where it says, okay, if this most of the time the API call is used this way, then that's probably correct. And then the Python code, which is the checkers on the right, goes through and tries to classify the majority of instances and then find deviations, find those outliers. So let's look at a really quick example before we dive in. Let's just take a basic example with the keygen, this init function, and free function, similar like malloc and free. So this is real code from OpenSSL, and you can just see it calls this init function and then calls free, and that is valid usage. And then here's another one where it calls this init function and then free. So after seeing all these, then the API stand is going to infer, okay, this is probably correct usage. And then it tries to find outliers, and it found one in OpenSSL, the same actually project that the API call originated from. So it was kind of an internal error there. And it found that it called this init without free, which can be pretty dangerous. So this was a real bug that API SAN found and reported to OpenSSL. And just really quick to go over the impact of, what's the point finding all this. You could get some pretty serious denial of service. You can get a pretty big memory leak on any server that uses the OpenSSL code, which could be a TLS or SSL server, or anything that's using just cryptographic applications that's generating keys, public-private key pairs, using um, any of the features that OpenSSL does. So OpenVPN was one I found that used it. And someone could make an exploit script that just constantly, just queries the API, the vulnerable code, and it would just keep generating basically just pointers that were just never freed. So you could eventually just fill up the memory. So you could get some pretty serious denial of service. So how does it actually work? We've seen an example, but how does it pick up on behavior like this? So it will scan over code and it'll take many different implementations as input. So if it's looking at an API, that init function, it's going to scan lots of functions that use it, and then more frequent patterns will be observed, and then the more frequent it sees it, the stronger the semantic belief. That's the term they use to mean that the it's not, I was going to say the model, but it's picking up on the correct semantics and how it should be used. And it used a threshold of zero point 0.8 to decide majority. And it focuses on 4 components. And this will come together a little bit on the next slide when we see it actually work in action. But it focuses on the return value, the arguments, the causality, and the implicit pre or post conditions. So Let's take a look at what that looks like. So take this function here. Let's say it was trying to dial in on the spin lock and spin unlock usage. What it's doing is it's taking a function and it's kind of unraveling it and building it into this tree structure. And the tree is more logic based here. So code could be structured differently. You can have if statement before, after, else if, switch, whatever you want to do. But at the end of the day, it will, in theory, be put into the same tree structure if it's the same logic, if it's the same code doing the same thing. And we see each of these have different return cases. They're all returning the same thing here because this is returning at the ends, but maybe there was returns in the middle. So it's trying to build these tree structures and then it's storing these in a database, and we'll see later, but that can take a lot of data to store. So let's look at the first component we touched upon there, the return values. Checking the return values can be critical, especially a language like C, which is mainly what this was working with, which was a lot of OpenSSL, a lot of Linux. So, functions like malloc, a lot of times it's returning the execution status. So, it's really important to be checking those, or just at the end of the function, like we just saw in the previous example. And APIs use return values differently. Sometimes a zero could be success or failure. Just really just depends on the developer and how they implement it. And enforcing the correct value check is difficult. I know GCC will yell at you. Hopefully, we use those warnings. Sometimes I ignore them, but one of the warnings, like for malloc and such, is it will make sure that the return value is being used. However, it can't enforce it's being checked correctly. It can check that that return value is being stored somewhere and something's being done with it, but it doesn't actually check if it's being used in a valid manner. So here's an example. We can see this was a valid bug that APISAN found. This fancy syntax here, I put it into pseudocode so it's easier to read if you're like me and don't like unnecessarily fancy syntax. So this kthread run function is returning this context thread pointer, and the developer mistakenly thinks that if this kthread run fails, it's going to return null, and null will be put into this pointer. So in that case, if that were the case, that this would return null, and then else it would return this error. However, this API call actually does not turn null on an error. It still returns a pointer. It's just pointing to nothing, so it's still a valid pointer, so it's not null. Essentially, whether or not it's valid, this is always going to be true, and it's always returning zero. So API-SAN likely saw, many instances of this function being called, except it had picked up, and this is invalid usage, it had picked up on the fact that in the majority case, and the paper cited this as error function that it should have been using or status. So it picked up in the majority case and then found, hey, here's this function, and when we unravel it into a tree, we're always getting this return zero value, which is deviant from the majority case. So it flagged this, and they looked into it and found the vulnerability and reported it. So that's return values. Let's look at the second component, which is arguments. Uh, arguments, sorry, arguments can be related. So something it looks at is, you have a function, there's arguments going in. That's great, but how can we pick up on patterns there? So one thing they noticed is that they can be related, and sometimes the same variable can be passed in. So here's a classic example with string copy. If you're passing in more bytes than the destination minus the source here, then it's actually overflowing. So you can get a buffer overflow. And a lot of times you can see something like this. So what APISAN is looking for is variables being passed into the same function multiple times. Something like this where it's a +1, or maybe it's using another function intermediately. So it's picking up on that and saying, hey, this n is being passed in 2 times here. There's clearly a relation here, and it's going to try and pick up on that. So let's look at a real bug it found. Here's one to PHP, and it's a code execution bug, which is obviously, doesn't really get more serious than that. And I went into the repo for PHP and found the real bug, and this was the author of the paper. So it was pretty cool. I went through his GitHub. We'll see a couple more of these throughout. So I actually got to go see the real projects and see the real code get fixed. So this here, we can see this change was pushed and then accepted by PHP. They found that most of the time, that there should have been another percent s, there should have been another string input here to this argument, and they found this case was a deviation from majority, and looked into it and found a bug. I don't know the specifics, but I'm assuming overwriting this string, past here, somehow they were able to inject code to get it to execute, or maybe that was the worst case, but it was accepted, it was valid, and this is the real commit to the PHP, which is really cool. So the third component is causality. This is your classic cause effects, A, B relationship. And the paper mentions that, direct causality has been studied. It's pretty easy, like a malloc and free. Even GCC has a warning for that, like I mentioned. But they wanted to catch more complex, more conditional causality. So this is a good example where we have this try unlock and unlock. And you need to unlock after try unlock, but only when it actually acquires a lock. So, a naive approach might say, wait, this try unlock is called and then it returns, but it doesn't actually acquire the lock. It only does that if because this has a return value. So only if it doesn't return a lock, then you need to call unlock. So this case, you do need to do it before you return. This one you don't. So there's a little condition there. This is the kind of conditional causality that paper's trying to catch. This is valid usage, but I just wanted an example to show the condition that, it's not always just simple A, B. It could be A, B if C. So component 4 is implicit pre and post conditions. So there's an example here from APISAN. There's an SSL get verify result function, which shows the result of the certificate verification. However, if there is no certificate, it returns this 509 VOK status, which I think is a little unintuitive, but that's how the function is implemented. And there is a get peer certificate, which must also be null. So this will get you the result, but only if this is not null. So there's two functions. You need to check both of them. There's, it could be a lot of different ways to do that. So the correct usage isn't really clear cut here. There's not one right way to do it. You could have a switch, you could have an if else, you could have two conditions and an if. So a little bit tricky here. Okay, and here's the pop quiz. So I hope you were paying attention on the previous slide. These are 4 examples from the paper. So pause now if you want. You can go back to the previous slide. One thing to note is, all 4 cases are using both of the functions. So it's not like they just completely forgot to call, like, example 1, where they just forgot to call free. It's using all 4 of them. So pause, try, and see if you can beat APISAN. Okay, let's jump right in. So the case 1 in curl, they get peer certificate, and they check that it's not null, and we're going to assume they do the right code in there, and then we get the value. So this one is valid because they properly check that it's not null. Case 2 with hex chat, they get the result and store. They haven't checked if it's not null, and it would jump into this case either way, and then it gets the peer certificate. So this is actually invalid usage, and was a bug the APISAN found and reported to hex chat. Case 3 is nmap. It gets the cert, and similar to case 1, checks if it's not none. Very, very similar logic here, and then it moves on. The only difference is it had this double check here, just in case, but it was unneeded. It was valid either way. And then this one's a little bit different than the first one. It calls this function right away, but it does have this check to make sure that it wasn't equal to that status, and it returns if so and moves on. So these are semantically different, but essentially the same. So it is the same thing. It is valid. So let's look at that hex chat fix. This is again pushed by the author, and you can see the hex chat, he authored it and they committed it. And this is the little note they had that the existence of the certificate did need to be checked, and they were not doing that in the current code. So pretty cool to see. And this is the real code fix. I was doing pseudocode in Python just for this previous slide, but this is what the actual fix looked like. And this was the vulnerable code. So here's the results from APISAN. You'll see a lot of great programs: Linux, OpenSSL, PHP, Python. pretty cool stuff. They have a lot of system crashes, a lot of denial of service, kind of malfunctions, heap overflow kind of things. Um, but they have some code execution, which is great. I think there's still one more. There's the Python one we can take a look at. Um, and then you can see the number of bugs. It's a great thing about automation. It found this instant 13 times in Linux, which is great. All the checks are bugs that were reported, validated, and patched. It was 2016, so I'm assuming these pending reports have since been resolved or closed. But in all, there was 76 valid bugs they found, and 69 of them were verified. Um, so pretty good stats. Really great work. I think they should be pretty proud of it. Here's a couple bonus bugs. I mentioned the Python one. This one's cool. It's on the Python website. Again, they cite the author. This was a heap overflow. They listed it as code execution on the previous slide, so I'm assuming they got the heap overflow, and it's vulnerable to code execution. And then here's one for OpenSSL. Again, I went through the author's GitHub. Really interesting to go through. Highly recommend it. He's got a lot of great stuff on there. Obviously, a lot of having commits to Linux and OpenSSL is pretty cool. So I'd highly recommend going through those. Some quick stats just about their research and performance. They obviously had a pretty strong server and a lot of RAM, which we'll get into the next slide. Maybe it could be holding the tool back a little bit. It did generate 40,000 reports. The way they did that is they said it ranks them on like probability, which is most likely to be vulnerable. And they just started going through the most vulnerable ones first. And if it was valid, then they reported it. They didn't have any specific stats on false negatives that I could see, or sorry, false positives. So because they didn't go through all 40,000 of those reports, but either way, the ones they looked through, finding 76 bugs, I think is very valid for some pretty high-end projects. So it ran 8 hours on Linux kernel is about 9 million lines of code and generated a 300 gigabyte database. And again, that database was the tree structures that the checkers have to go through. So it generates a lot of data for 9 million lines of code. Um, and it takes approximately 6 hours. So again, and here's the lines of code for the project. So API stands about 9,000 lines of code. This is the database generator in C that generates that kind of tree structure and the semantics. That's what was going into this 300 gigabytes. And then the checkers are kind of categorizing them, classifying what's majority, and then identifying the outliers. So 9,000 lines of code, which I think is pretty impressive. I would say, compared to all of these projects that are millions of lines, for the work they did. So overall, probably well written code. And where does API stand today? This was what I was really curious about after, seeing a lot of success. It is definitely a little outdated, not widely in use. I couldn't find really any modern instances, not a lot out there on it in use, but the paper is from 2016. I'm assuming now any research into this field is probably going to be mostly focused on machine learning to detect these semantics or tools like SemGrep, which I'm using in a different project. SemGrep is probably a little faster and more lightweight. That's based on rules, build rules and just simple YAML files, and those you can build custom rules that will just scan through code and identify instances. And that isn't going to have to go through and generate a tree every time and generate this ginormous database. The only problem is you have to create the custom rules, which is obviously the hard part. So definitely a trade-off. And here is the repository. It's got 63 stars, which is pretty good, but you can see that the code's very outdated. Really hasn't had a lot of updates, any updates in the past 4 years. So I'm sad to see. It looks like it's fallen out of use a little bit, but I think my advice there would be if people aren't looking into it and aren't using it, and if it's not being run too much, I would say go try it. There's a lot of open source projects that are releasing a lot of new code. I bet, if they found 76 back then, I'm almost sure if you ran it now on some big open source projects and looked and tested enough of those reports that it generates, I'm sure that there's some bugs out there to be found. You can get a CVE with your name on it, or just a patch you can commit on your Git. So I think it's really cool, and I'd recommend looking into it. Key takeaways from me: API Sand's obviously great at finding API misuse bugs and using the majority rules, semantics checks. I think is a really interesting way to do it. I obviously had some great success. And key takeaways for developers when implementing an API: check documentation, but also check example usage. Don't be the outlier. If you're not sure how keygen and ish function and a free function work, read the documentation, go check some other projects, don't check one. But if you find that most projects are doing it the way that you're doing it, then you're probably not the outlier. Uh, so either everyone's doing it wrong or it's the correct way to do it. So I would recommend that for developers. But bonus takeaways from me, my kind of biggest takeaway from all this was that it wasn't machine learning. It was generating, it was training, almost training on all this data, but it wasn't any machine learning. Um, but it was pattern recognition. It was anomaly detection, which nowadays, again, this would almost always be researched into with AI. But I really like the fact that they, created their tree structure. They came up with the four components that they wanted to look at that they knew would be effective. When again, a lot of times with AI, you just tell it to run off and do its own thing and come up with its own four components. I like that they picked the components that they knew would be indicative of correct usage. They created their own tree structure, and then they kind of did their own training in a way. So I thought it was a really cool alternative to what seems like an AI approach. Um, so I think these are all some good takeaways to take away. And here's the research paper. I'd recommend reading through it. I uh, definitely had a lot of fun reading through the GitHub, reading through a lot of the reports, especially big names like Linux and OpenSSL and Python. So I'm very glad I researched this project. I think I worked a lot. I learned a lot, and thank you to the researchers. And I hope everyone enjoyed. Thank you.